In this tutorial, the new RC6 module will be presented. This module is designed for the stress-strain analysis of reinforced concrete sections according to Eurocode and SIA code. It can take into account the applied reinforcement, the nonlinear behavior of the concrete and the rebars, as well as the cracking of concrete. The stress-strain state of the concrete and rebars can be used to verify the structure in various serviceability limit states. The stress ranges can also be calculated with RC6 for fatigue verifications. Moreover, the module can help to visualize the stress-strain state also in case of ultimate limit state, after the cross-section is designed with the RC2 module. In the next sections, the new features of the RC6 module will be presented through a prefabricated reinforced concrete hull with crane track, using the Eurocode standard. The one-bay reinforced concrete hull is 20 meter wide, 12 meter high, and 48 meter long. The distance between the main frames is 6 meter. The main beam is a 150 centimeter high pre-stressed T-beam. The columns have a cross-section of 40 x 40 centimeter and 40 x 80 centimeter, while the dimensions of the rectangular longitudinal beams are 40 x 70 centimeter. The hull is designed with a reinforced concrete crane runway to serve a 10-ton crane. The crane runaway girders are also rectangular cross-sections of 40 x 60 cm. The main beam has a concrete material grade of C40/50, while all other elements are C30/37. The beams are single-span girders. The column bases are clamped. Bracing is applied at both the front and rear parts of the hull to transfer the longitudinal wind and crane forces to the fundament. All structural elements are modeled with beam elements except for the bracing, where truss elements are used. The eccentricities are taken into account with rigid links. Flexural hinges are applied at each end of the beams. In order to be able to apply the pre-stressing properly on the main beam, translational hinges with a small stiffness are used in the global x-axis to avoid force transfer in this direction. The following load groups and load cases are defined for the analysis and design of the structure. We have permanent loads, such as the weight of the structure, the weight of the wall panels and the roof load. A tensioning load group is defined for the pre-stressing of the main beam, and we have also the typical meteorological loads, the snow load and the wind loads. Two crane load groups are defined as moving load groups. One is for the ultimate limit state to design the crane runway beam. The other is for the fatigue assessment. Once we define the load groups and load cases, we have to define the critical load group combinations. In this table, we can choose which load groups can be combined with one another, using the partial and combination factors of each load group, to arrive at the critical results. In our case, the fatigue load group does not need to be considered for the critical combination. Therefore it can be unchecked. In some situations, we need more than one load group for the same action, if it is described with multiple groups of loads. Such case is the crane load itself, where Eurocode, for example, defines 10 loading situations. For the sake of simplicity of this example, we consider only the first load group, which is authoritative for the design of the crane runway beam. However, the final design should contain all 10 load groups, and in the critical load group combinations table the simultaneous action of them has to be excluded. Now let's see how we apply the different loads on the structure. The structural weight is calculated automatically by the software. The weight of the wall panels is applied as line loads along the length of the columns. For the roof load and for the snow load, A load panel is defined to automatically distribute the surface loads onto the main beams. The roof load is 1.0 kN per square meter, while the snow load is also 1.0 kN per square meter. We can also ask the program to show the load distribution scheme as well as the derived line loads on the main beams. This way we can check if the distribution corresponds to that of our expectations. At the wind load definition, we chose the traditional way of distributing the loads as line loads onto the columns. As a simplification, only the columns are loaded. Furthermore, the wind pressure and wind suction are indifferent from the wind direction. All four wind directions are simulated with a wind pressure of 0.4 kN per square meter and a wind suction of 0.25 kN per square meter. The pre-stressing is modeled only for one beam, which is authoritative in the middle of the hull. The pre-stressing is applied with the help of the PS1 module. This module is designed for post-tensioning applications, but it can help us to define the pre-stressing tendons and to automatically calculate the external forces caused by the pre-stressing. In the PS1 module, we can easily define the position of the tendons using the longitudinal or cross-section view in case of the graphical input, or by using the tabulated input option. In this example, we apply 12 pieces of FP100 per 1770 tendons. In case of pre-stressing, the tension loss at the end of the tensioning process is nearly zero. This behavior can be obtained by setting the relevant tendon properties to 0. At the tensioning process, we leave out the anchoring loss and we apply a 75% tensioning from both sides. We can check the results on the Results tab. The tension force is constant without additional loss along the beam. And as we can see, there is no additional vertical internal force, since the tendon is straight. If we go back to the model, we can see the external forces at both ends of the beam. The normal force represents the tensioning force at the time of pre-stressing, and the bending moment is caused by the eccentricity of the tendons. The PS1 module calculates the tension loss during the lifetime of the structure, but since this loss is related to a post-tensioning process, it cannot be used in our example. The loss in pre-tensioning is only estimated and a factor is used to convert the T0 results to the T1 time step. Let's move on to the crane load definition. Typically, overhead traveling cranes have a hoisting class of HC3 or HC4 and an S class of S6 or S7 for fatigue verifications. In our example, the hoist load is 10 ton, as well as the weight of the crane. And we have a single 2-ton crab. Considering a hoisting class of H, C, 3, and an S class of S, 6, leads to 195 kN characteristic load on one side, and 85 kN on the other. The crane has 4 wheels with a distance of 2 meters. The crane load is applied with the help of the moving line load definition. The wheel loads are concentrated loads, but we could apply distributed loads as well. We can define the type, eccentricity and the longitudinal position of the load. To simplify the example, we will only use vertical loads, but the other simultaneous horizontal Fx and Phi components could be defined as well. The position of the second wheel is 2 meters. The crane cannot leave the crane runway beam, so we use the crane runway mode. It is sufficient to use a one-way pattern, since the wheel loads are identical on one side. In the next step, we define a load path by selecting the relevant crane runway beams and also the start and end point of the path. We need a smooth load distribution. So we set the number of divisions to 100. The software automatically creates 100 load cases for the crane load in the 100 different positions. For the fatigue verification, a reduced wheel load of 88 kN and 37 kN is used. We define the fatigue crane loads in the same way as we did for the characteristic load. We can change the parameters of the moving load anytime. For example, the number of divisions. And the software redefines the load cases automatically. In addition to the automatically calculated critical combinations, we can also define custom combinations for various purposes. For example, we would like to check the uncracked state of the main beam in the frequent combination at the time of pre-stressing as well as at the end of the lifetime. The loss in pre-tensioning is estimated to be about 30%. Therefore, a factor of 0.7 is used for the T1 time step. The crane fatigue load is a unique load group. For fatigue verifications, we have to combine the moving load with the permanent loads. This can be done in the custom load combinations by load groups table. Here, it is sufficient to define which load groups are combined with one another, and the software generates all the possible unique load combinations, so that we do not have to do it by hand. After the definition of the load combinations, we can start the static calculation. To present the features and capabilities of the new RC6 module, 3 structural elements will be checked. The pre-stressed main beam in the frequent combination to check the uncracked state. The column in the characteristic combination to avoid excessive cracking of the concrete and plastic deformation of the rebars. And the third element is the crane runway beam, where we will design and check the beam for fatigue. First, let's see the main beam. If we choose the predefined load combinations in T0 and T1, we can see that the tension from the bending moment is authoritative at the beam end in T0 and in the middle in T1. Now we check the stress-strain state of the beam. The RC6 icon is located on the Reinforced Concrete Design tab, at the right end of the icon bar. We select the main beam to start the analysis. It is important that the analyzed structural element has to have a column or beam reinforcement defined with the RC2 module. Otherwise the analysis cannot be started. In the main window of the module, the first thing we see is the cross-section with the compression zone, the strain diagram as well as the stresses in the concrete and in the rebars. On the right side, the module provides information about the analysis parameters and about the main results, such as the actual and calculated internal forces, the calculated strain in the center of gravity and the curvatures about the local Y and Z axes, and also the depth of the compression zone and the lever arm of the tension force from the external compression point. Before checking the results, we have to set the analysis parameters. We can choose from the standard material grades, but they may differ from those specified as reinforcement parameters. We can select which internal forces are to be considered and we can modify the seismic coefficient as well. The software provides 4 material models according to Eurocode. These are the bilinear, parabolic, nonlinear and custom material models. The latter allows us to define tensile strength. Therefore it is appropriate for checking the uncracked state of the concrete. The program automatically defines the standard stress-strain functions based on material grades. The rebar behavior is modeled by a bilinear material model. The last option, the filtering, defines which component should be used to select the critical solution in case of envelope or critical combinations. In the drop-down menu, we can select the source of internal forces, which can be taken from any load case, load combination, envelope or internal step of a nonlinear or dynamic analysis. First, we select the combination for the pre-stressing in the T0 time step. The software shows the middle cross-section of the beam by default. The pre-stressing is effective, the whole cross-section is under compression, but the stresses never reach the limiting values. We know that at the time of pre-stressing, the end section of the beam may be critical. We can change the position for analysis by entering the required X coordinate. The upper external fiber of the concrete is under tension, but it does not reach the limiting value of 1.7 MPa for the C40/50 material grade. Therefore, the beam remains uncracked. Other values are also under the standard limits. Now we check the stress state of the middle cross-section at the end of the design life T1. The lower concrete fiber here is also under tension. But again, all stresses are lower than the limiting value. Thus the uncracked state can be verified. Click on the table icon to display the results in a tabular form. Detailed results are provided for all analyzed internal force combinations, if an envelope or combination of load groups is selected. The tables as well as the result diagram can be printed directly or copied and saved for documentation. The column is designed with the RC2 module, where the reinforcement parameters and reinforcement are also defined. The utilization is about 70%, meaning that the column has additional reserve for the not considered crane horizontal forces. Now let us see the stress-strain state of the cross-section at the foot. First, we set the analysis parameters and then select the characteristic load combination. Now we can check if the concrete compression and rebar tension is acceptable. All values are under the limit. Therefore, the requirement of this SLS is fulfilled. We can also define custom internal forces. An error message appears if the normal force biaxial bending point is outside the load-bearing surface. Otherwise we can check the tabulated results. Let us check the other column at the front, which can obtain biaxial bending due to direct wind loads. Because of the biaxial bending, the local axis is now inclined. We can rotate the view parallel to the cross-section or to the local axis for a better overview. The stresses are again acceptable. Actually, this check may be critical rather for taller buildings. Nonetheless, it has been shown that this check now requires only a couple of minutes with the new RC6 module. In the crane runway example, the first step is to observe the authoritative internal forces and design the beam with the RC2 module in the ultimate limit state. We set the reinforcement parameters. We use 20 mm rebars, 8 mm stirrups and a 3 cm concrete cover. At the Actual Beam Reinforcement tab, we can automatically apply the program calculated reinforcement to fulfill the requirements of the ULS. That means 5 rebars at the bottom and 2 rebars at the top. For simplicity, we apply the same reinforcement along the whole length. The applied reinforcement appears in the schematic cross-section shape. Let's see if this reinforcement is sufficient for the fatigue verification. In order to verify the rebars, both the fatigue strength and the stress ranges have to be transformed to the 2 million cycle level. The design fatigue strength of the rebar at 2 million cycles is 123 MPa. The damage equivalent factor for S6 class cranes considering a slope factor of 5 of the SN curve is 0.871. Rearranging the equation provided by Eurocode, we obtain a maximal allowable stress range of 141 MPa. The stress range is calculated as the difference between the stresses caused by the permanent loads and by the fatigue load group. If we click on the beam and select the fatigue combination, we can determine the position of the maximal bending moment. This is our critical cross-section for the fatigue verification. In the RC6 module, we set the analysis parameters, then read out the maximal stress in the rebars. We do the same for the permanent loads, which is here only the structural weight. The calculated stress range is therefore 267 minus 34, equals 233 MPa, which is way more than our limit of 141 MPa. That means, we have to increase the number of rebars, even if they are sufficient in the ULS. Let's go back and apply 4 more rebars and repeat the fatigue check. The stress range is 158 minus 20, equals 138 MPa, with which the fatigue verification is fulfilled. In this example, the fatigue requirement is stricter than that of the ULS, and that leads to a less economical design. In this case, a pre-stressed beam would be a more favorable alternative, since it reduces the tension in the rebars and also increases the fatigue strength of the concrete. In this tutorial, the new RC6 module is presented through an RC Hall example. It has been shown how the module can accelerate both the preliminary and final design process in order to arrive at economical solutions. Since the module is integrated into the main software, the stress-strain state of reinforced concrete beam elements can be assessed in a couple of minutes for all the relevant load cases and load combinations. The results of the analysis can be used for various serviceability limit state verifications as well as for the fatigue evaluation of RC cross-sections. With AXISVM software there is no limit you can make.